Hi, I'm Benjamin Herman from the Department of Mechanical Engineering at Universidad de Chile. And this is a video abstract for my recent work titled Interpolatory Input and Output Projections for Flow Control. This work was done with this fantastic group of colleagues and was recently published in the journal Fluid Mechanics with open access, so I'll leave a link to the full paper in the description below. So the way this talk will follow is just by dissecting this title. So first I will talk about what are input and output projections. Then I will explain what do I mean by interpolatory projections. And finally, I will address why we think this is useful for flow control applications. Okay, so let's start with input and output projections. And our starting point is a linear dynamical system that has either high dimensional inputs or high dimensional outputs. Okay, and what input and output projections do is reduce the number of inputs over the number of outputs. And the way this is achieved is by projecting these high dimensional inputs or outputs onto lower dimensional subspaces. Okay, so output projection was developed first by in the work of Rowley. Dergam, Zip, and Robinet formalized this idea of input projection later. And one thing you might be wondering is, well, what's a good subspace, or how do I build this projector to get my high dimensional inputs into a lower dimensional subspace? And the idea is that you build this projector such that the response of this modified system, so here I have the projection, so you want the response of this system to be close to the response or the output of the original system. So you want to build a projector that achieves that. And the same goes for output projection. So you want to, here you're projecting just the output, but you want this projected output to be close to the original output, or to the output of the original system. So the question now is, well, what are good subspaces to project onto? And we're thinking about systems with full state inputs and outputs, such as a fluid flow that can be disturbed anywhere and can be measured everywhere. Okay, so that's the kind of systems we are interested in. And for fluid flows, we have this fantastic tool, which is resolvent analysis, and that gives us sets of input and output modes, or forcing and response modes, that are optimal at producing high input-output gains at specific frequencies. So resolvent modes kind of solve the problem that we want of getting representative inputs and outputs, but these inputs and outputs are tailored to specific frequencies, so they are optimal only when forced harmonically in time at specific frequencies. And we would prefer to have modes that are representative across all frequencies, or at least across a wide range of frequencies of interest. And you still can achieve this using resolvent modes. So here I'm just doing hand-picking some resolvent modes at frequencies that have high gains. So this is the gain, and I'm cherry-picking a few resolvent modes so that I build this basis of flow structures. So these are inputs, and these are outputs that are representative across a wide range of frequencies. Okay, so these are now fixed flow structures that do not depend on the frequency. So we have basis of input and output modes that we could use for input and output projection. However, there is a much more principled way to achieve this, which is using the Gramians. So the Gramians are matrices that come up in control theory, and this is the observability, this is the controllability Gramian, so this matrix is right here. And this is for the case of full state inputs and outputs. And the eigenvectors of these matrices are also representative inputs and representative outputs. These are known as observability and controllability modes, and for the case of full state inputs and outputs are also known as stochastic optimals and empirical orthogonal functions. And you can think about these modes as these are the sets of inputs that optimally can sustain the variance of the system under white noise. And these are the modes that optimally can account for the variance in the system forced by white noise. Okay, so and I'm plotting just the leading observability modes and controllability modes, and you can see that they almost match one-to-one to this handmade selection of resolvent modes. So there is definitely a very nice connection between stochastic optimals and empirical orthogonal functions and resolvent modes. So this connection has been well established, but we do a nice work in the paper of reviewing this nice connection. So if you want to learn more about that, I invite you to take a look. Okay, so observability and controllability modes throw away that frequency content information that is great about resolvent analysis. But for input and output projections, we actually don't care about that frequency information. So this is a much more principled approach to get what we want, which are these bases for projection. Okay, now that we have bases, let's talk about building projectors. So conventional input and output projections use the modes that I just presented to build orthogonal projectors. So this is our good old friend, the orthogonal projector. And what it does is, when you hit a vector x with an orthogonal projector, you get something that's as close as possible to the original vector, but that now lives in the span of your basis vectors. Okay, and that's nice. Now let's talk about a more fun projector, in my view, the interpolatory projector. So we didn't come up with this terminology. So this name, interpolatory projector, was first introduced in the discrete empirical interpolation method paper by Chaturanthapat and Sorensen. So this is the DIME paper. And the term has been adopted by other authors as well. So that's why we're keeping with it. So an interpolatory projector is an oblique projector with the additional property of exactly preserving some of the entries of the original vector. Okay, so the way you build it is, so you still need a basis of modes, so your basis V, and now you need this P matrix, which is a sampling matrix that contains columns of the identity matrix. So this is a sparse matrix that selects entries in any vector it hits. Okay, so when you hit a vector x with this interpolatory projector, you get something that exactly matches the original vector at some of the entries. And it messes up the other entries, but it doesn't matter because these other entries are actually in the span of your basis vectors, just as like for the orthogonal projector. Okay, and okay, so we talked about how we're picking our basis vectors for input and output projections. Now let's talk about how to pick our sampling matrix P. And this is a very important step because we want this inverse here to be well conditioned so that this interpolation is actually close to the original vector x. So you can see that what this interpolatory projector is actually achieving is, from just a subset of entries of the original vector, we are interpolating the full dimensional vector. Okay, so and you could do a formal optimization to look for the best columns of the identity to build P so that you get the best reconstruction possible for some set of vectors x. However, this is a costly optimization because it's a non-convex problem and it requires a brute force search. So it doesn't scale to higher dimensions. And there are many greedy sensor selection algorithms that bypass this intractable search in higher dimensions, so that you get something that's close to the optimal, but without doing the formal optimization. And so one of the methods is the DIME method. You could use the pivoted QR method introduced by Kritika Manohar and by Dermagani Gugerjin in the context of hyperreduction for dynamical systems as well. Okay, so in this case, we're taking the pivoted QR approach because it's very simple to implement and it's giving us great results. But you could swap it for another method if you prefer. Okay, so this is our main contribution. We now have all the ingredients to build interpolatory input and output projections. And just to remind you, the idea is that we want to reduce the number of inputs or the number of outputs in a dynamical system, but we want to do it in such a way that the reduced, this lower dimensional input is actually a subset of the original high dimensional input. And the same goes for the output, okay? So that's the main contribution for our work, along with the examples of how this is useful. So we take a look at a few examples in the paper, and I will show just two in this talk. So the first one is we can learn where to place sensors so that from a subset of the input, so from partial input information, we predict the response of the full system. We can do open loop control design. So we can design an open loop control law, so to do feedforward control, so that we partially mitigate only the most meaningful disturbances, so the disturbances that actually do any harm in the dynamics or that produce an energetic response. So we can do this feedforward control where we focus on mitigating only the important parts of the disturbance. In this case, a disturbance field or a high dimensional disturbance. Okay, and for the output projections, well, what we propose is to do sensor placement for state reconstruction or for output reconstruction. Okay, so I will go into two of the examples just to give you an idea. And the first one is for interpolatory input projection. So we're projecting inputs or a forcing field in this case. So let me first introduce the problem here. So this is the Ginzburg Landau equation. This is the linearized Ginzburg Landau equation, which is a PDE. So this is space, and this is the temporal response of the system. And this is a linear system that's being forced by white noise. So this is the forcing signal. This is the white noise forcing. So what we want is to measure this forcing field only at a few spatial locations and be able to predict the energetic parts of the response. Okay, so just with 8 sensors, so measuring this field at 8 locations, we can interpolate the forcing. So this is our interpolatory projection of the forcing, and we can use this projection to predict the response. So we're now predicting the response to this forcing field, which is not the original forcing, is what we are interpolating from our sparse measurement. And this is what we predict. So we capture the high energy structures quite well. Okay, and so if you see the projected forcing doesn't look exactly like the forcing, and we're not trying to do that because not all components of the forcing affect the response equally. So the dynamics here act as a filter, and these are the dynamically relevant parts of the input. So that's the only thing that we care about reconstructing well in order to predict an accurate response. Okay, so here are some more quantitative results for the same example. What I'm showing here is our performance metric, which is the L2 norm error of the response. So this is energy integrated over time, and it's normalized for a very long simulation with white noise forcing. And keep in mind that we're comparing the error in the response, so not in the forcing, because we're not trying to reconstruct the forcing. We're trying to reconstruct the forcing that's responsible for sustaining the response, which is not the same. So this dashed line here is the response, the performance that we get with our interpolatory projection, so as a function of the number of modes in our reconstruction and also the number of sensors. So with our sensors, this is the error that we get, and this lower bound here, this solid curve that you see here, is the orthogonal projection onto the same basis modes. Okay, so we follow closely, quite well, the orthogonal projection, although we are only using the values of the actual inputs at a few locations. So we're doing this interpolatory projection, and we still get fairly close to the orthogonal projection. And these are where the sensors land with this greedy sensor selection algorithm that we're using. So for a number of R sensors, this is where the sensors land in space. And this is very similar to what has been found in a different context in other works for the same system. So in these works, they have looked at sensor placement for feedback control, whereas here we're predicting their response from a subset of inputs, which is a different problem, but the optimal sensor locations are very, very similar. Okay, and the last example that I will be showing here is this interpolatory output projection now. So we're looking at the output projection, and this is a turbulent flow in a minimal channel. So this is the smallest channel that exhibits turbulent flow at RE tau 180. So we have these direct numerical simulations here. And what we're trying to do is just from a few measurements of the velocity field, try to reconstruct the full velocity fluctuation field. Okay, and I'm showing the results here with a rank R projection, so with the rank 20 projection, 200, and 800. Okay, and for a rank R projection, I'm using R modes. I'm using R sensors that are strategically placed, and I'm complementing these with 2 R random sensors to improve the reconstruction. So here we have 60 sensors, 600, and 2400 sensors, which may sound like a lot here. So in this case, the reconstruction is quite good. You might think that 2400 sensors is a lot, but it's still 1.5% of the information of the full state. So the DNS, the number of degrees of freedom, is still much higher than 2400. Right? So from around 1.5% of the information, we get this reconstruction, which is quite great. And keep in mind, this is not a data-driven method, so we don't need any data snapshots to do this. This is fully equation-driven. And another important point is that we're not even doing state estimation. This is snapshot-to-snapshot state reconstruction. So it's the reconstruction is independent at every time step. So this information about where to place the sensors could be also used for state estimation, where you leverage the time history and can probably get much better estimates of the flow field. So that's certainly a direction of future work. Okay, and here are the quantitative results for that example. The metric is similar as before, so it's the energy error integrated over time, so the L2 norm. And so there's a few curves here. So again, the axes are the same, so this is our performance metric, where lower is better, so this is error. And this axis has the rank of the reconstruction, so the rank of the projection. Let's start from the top. So this that dashed line is the interpolatory projection using just random sensors. So this is 3R random sensors for a rank R projection. And well, the reconstruction area is not great, but we gain a lot. We reduce the error drastically if we use these strategically placed sensors with pivoted selected by the pivoted QR algorithm. Okay, so this is how we do with the sparse sensor placement algorithm. And now this solid curve here is the orthogonal projection, which is analogous to using measurements everywhere. Okay, so this solid cyan line is the best that we're going to do by projecting onto this same basis. So we follow that. We see that the important part is that with our interpolatory projection, we're following not that much behind of the best that we can do given the basis that we're using for projection. And now this pink or this magenta line here is the projection onto POD modes. Okay, this is orthogonal projection onto POD modes. So this is the optimal linear subspace for projection. It's actually optimal for this exact metric. So this is the best that we're going to do with any projection. So again, with these modes, the modes that we're using for projection here, to remind you, are the controllability Gramians of the mean flow linearization. These results do not lag that much behind the projection with POD, and getting fully converged POD modes for a turbulent flow can be very expensive. So to achieve this, we only require information of the mean flow and the mean flow linearized equations. So this is fully data-free in that sense, which is great. Okay, so the big picture here is that we start with a dynamical system that has either many inputs or many outputs, and we want to reduce the number of inputs or outputs. And one way to do that is with input or output projections. The way that works is that you project the higher dimensional inputs or outputs onto lower dimensional subspaces. Okay. Now the main contribution of our work is to do this, but with interpolation. And what we gain by doing that is that now our low dimensional inputs are an actual subset of the higher dimensional input. And the same goes for the output. So the low dimensional output is an actual subset of the higher dimensional counterpart. And what we can do with this is that, well, we can now predict the response of the system only by knowing a subset of all the inputs that are acting on the system, or we can reconstruct the full output only having access to a subset of all the available measurements for the system. So that's the main idea. Okay, so the code is available on GitHub to reproduce all of our results, and I will leave a link in the description below to the full JFM article. Thank you for watching.